So, good morning. Today we start some lessons which will cover some fundamental aspects of fluid mechanics. And the reason is that in the class of fluid machinery you need to get familiar with some concepts of fluid mechanics first before moving to the fluid machinery topic. At the same time, this set of lessons is intended to double the introductory material for the class of fluid mechanics, but taught in English, so that you can practice at the same time English and you can brush up a few things of fluid mechanics. Good. So, as the word says, fluid mechanics, we need to introduce what a fluid is. Now, each of us somehow has some intuition about what is a fluid. Definitely you know that a block of stainless steel is not a fluid, while a glass of water or your favorite drink is a fluid. However, engineers, scientists in general don't have to rely only on intuition, but rather on solid definitions, on operative definitions which allow them to operate on mathematical relations. So our idea of a fluid must be laid on more solid grounds. So how do we put our idea of fluid with respect to the organization of matter? This is already strange, because since our primary school we are taught that matter can show up in three distinctive states, which is solids, liquids, and gases. Now, a fluid can be either a gas, a liquid, and sometimes even a solid. Now, since at least the basic idea of solids, liquids, and gases has to do with the shape and volume, it is clear that this idea of fluid cannot be firmly related to shape and volume. There must be something different behind. Of course, there are different states of matter, like plasma, which is ionized molecules and atoms, and even that one has to do with the concept of a fluid. So just to lie down some basic idea, let's make a very simple example with something that definitely is not a fluid. So we can have a block of some material, and this material is fixed to the bottom of a table or some plane, and then we apply on the upper surface a shearing force. So by shearing, I mean that the force is tangent to the surface. Now, we know that a force applied to a surface generates a stress. So we can call this tangential stress tau, and this is nothing but the ratio between the force and the area. Okay? So the area, if we make a perspective sketch of this block, okay, so let me use colors. So this face is just this face that we are seeing from a lateral view. Then what I call area is nothing but this surface, and the force is applied tangential, So this is the force. Now you should be aware that the force is a vector. The area is characterized by a normal vector, and so this tau, as a matter of fact, is a tensor. But we will disregard completely all this tensorial nature of the stress. We can just restrict to the modulus of the force, to the area of the surface, and so we will have just one single component of the stress tensor, which we can think of as a scalar quantity. Okay? So this is just to be precise. So we apply this tangential forcing to the surface. What do we expect? Well, if we just look with the naked eyes, and if this is a solid, like concrete or stainless steel, the most obvious answer would be nothing happens. Because when I apply a shear stress, even if I'm strong and well-built, well, I cannot do anything to this material which I can see with my naked eyes. However, if I'm very careful and I design an appropriate experiment, well, I can see that this material is in fact deforming. So we start from a cuboid, we start from some rectangular shape, and we end up in a parallelepipedic block. So what happens is that the initial vertical surfaces become a little bit slanted, and there is an angle which we can call angular deformation. Now, if I'm lucky enough to select a simple material, simple in quotes, what I can write is that tau is directly proportional to the shear angular deformation, or if you wish, the angular deformation is directly proportional to the shear stress. So what does it mean? I put some effort to deform my material and I get one angular deformation. I double my effort and then I double the angular deformation. Well, this is quite expected. Now, proportional doesn't mean equal. If I want to quantify, then I can write that tau is equal to some constant times the angular deformation. And this constant depends on the material, so whether it is stainless steel, concrete, wood, and so on, and on the state of the material. So its temperature, the pressure that it has to withstand, and so on and so forth. Well, this is not, of course, a general behavior. There are some materials which comply to this behavior, and the materials behaving in this way are called elastic solids. Okay, so we can write it here: elastic solids. Actually, even more precise, linearly elastic solids. And of course, these are not fluids. So how can I write? How can I parameterize this behavior in a graph? Well, first of all, I can imagine that on a set of Cartesian axes, I put time, and I put tau, and tau is the shear stress which I apply to the material. So I can imagine that I start from this undeformed and stress-free material up to some time, for example, this one, T1. And so before I apply any forcing to the block, there is nothing. Nothing, I mean, I'm not deforming the material. So this means that if I put another set of axes here, So here I have time, and here I have the angular deformation gamma. Up to T1, the angular deformation is 0. Maybe I can use some colors for this. So the angular deformation is 0 until the tangential stress is 0. Then, at t equal to 1, all of a sudden, I apply some tangential stress, and then, consistently with this equation, with this relation, I get some angular deformation, which remains constant in time as long as the shear stress remains constant in time. Then, at time, let's say T2, I decide to relieve my external forcing, which comes back to 0, and accordingly to this relation, also the angular deformation comes back to 0. Now, as you can see, there is an instantaneous relation between angular deformation and time. So, whenever I change the external forcing, instantaneously it changes also the angular deformation. There is no delay. And of course, this is not true in reality, but we will see that the time it takes gamma to adapt to tau is within the microscopic time scales, so order of nanoseconds or even less, and so usually we should not be concerned with this delay. Another important piece of information is that whenever we remove the external stress, so when tau is brought back to 0, gamma goes back to 0 as well. So what does it mean? I have this block, I deform the block, and when I remove the external stress, the block recovers its initial position. So once I have removed my external stress, there is no memory of what has happened to the block. Okay? These are elastic solids. Possibly you have already met these materials in other subjects, but this is just introduced to stress the difference with a fluid. Now let's see what happens if we perform an identical experiment, but to a different material, which we will classify as a fluid. So again, we have a block of some unknown material. This block is such that it is fixed to a plane, so that the block has to stick, cannot move with respect to the plane. And then we apply externally exactly the same tangential stress. What do we get now? Well, if you run this experiment, you see that after some time, let's say t prime, this is the angular deformation you get. Actually, these two angles should be identical. Okay? So this would be some angle, which we can call gamma prime, but this is what you get at some time t prime. Then you wait, and at another time t second, you get another angular deformation, which you call gamma second. Now gamma second is the whole angle, okay? It's not just the variation. And then you wait another time, and you see that you get another angle gamma third, and so on and so forth. So if you put some soap, some water, some honey between your hands, and you start shearing, as long as you keep shearing, you keep deforming, and you never get stopped. If you take in between your hands, your eraser, what you use to erase what you write by a pencil, and you start shearing, you can deform a little bit, but by maintaining your shear stress, you cannot deform anymore your eraser. Now, the eraser is an elastic solid. Your soap, the honey, water has this behavior, which we characterize as the behavior of a fluid. Now, let's see what is the main difference. Now, the external load is exactly the same. Up to T1, I don't apply any external stress. Then in between T1 and T2, I apply this external shear stress. And then at time T2, I decide to remove instantaneously my external shear stress. So let's see what I get. Now we will put gamma here. We put here time. And then I have again here T1 and here T2. Good. Now, what do I get as angular deformation? Well, until I don't apply anything, my block will be undeformed. So the vertical faces will be vertical and the angular deformation, according to this plot, to this graph, is 0. But then, when I start shearing, the angular deformation starts increasing. And the more I shear, the more the angular deformation augments. And so I have a linear increase of the angular deformation up to time T2. Then, at T equal T2, I instantaneously remove the deformation. Then what happens? Well, I recall that for an elastic solid, when I remove the external load, the material recovers its original position. What do I expect for a fluid? Well, I think a little bit. I have some honey in between my hands. I start shearing, then I relax my muscles. Well, I don't expect that the honey pulls back my hand at the original position. And in fact, this is what happens. So when I remove the external load, tau, the material remains frozen at its latest configuration. So it means that it maintains, for good, the latest angular deformation. So I can see that there is a stunning, a striking difference between the two materials. So one, when loaded, responds with an angular deformation, which is constant in time. Another one, when loaded, responds with an angular deformation that increases linearly in time. So the two materials are quite different. Now, we like to handle constant quantities. We really love to write relations for quantities which do not change in time, because they give the simplest possible description. Now, if I think a little bit, there is something that indeed remains constant in time here, which is the slope. Okay? So, if I take a quantity like d gamma dt is nothing but the slope of this line, but since this is something that increases linearly in time, the slope is constant. It's nothing but the angular coefficient of a straight line, and this is called the angular deformation rate. So the rate at which the deformation angle increases in time. Good. So what I could do, I could draw another plot T1, T2, in which I do not focus on the angular deformation, but on the angular deformation rate. So how does it look like? Well, this is a horizontal line, and so before I apply any external load, the angular deformation rate is 0. But then I start shearing the material at a constant rate, and the slope of this line is constant. So I get some constant line that when the external load is removed at time t2, so at this time, the deformation comes back to a constant value, which means that its rate is 0. And then, as you can see, just by focusing on another variable, I recover a behavior which is very similar to this one. So what for an elastic solid is the angular deformation, for this material, which we will refer to as a fluid, is the angular deformation rate. Well, once I have a constant quantity, I can play the same game that I've played here. So I can write something like that the external shear stress is proportional not to the angular deformation, but to the angular deformation rate. And if I want this proportionality to become an equality symbol, I can write tau equal to mu gamma dot. And this mu is called the dynamic viscosity of a fluid. So I know that the shear stress is directly proportional to the angular deformation rate through a constant which depends on the material. So the value of mu depends on the material, on the fluid, and on the status of the material. So on the temperature at which the fluid is operated, and at the pressure at which the fluid is operated. Good. So to recap, what is the difference between an elastic solid and a fluid? Now I've left some space here and here because we need to add some adjectives to this known fluid. So the main difference is that you take the material, you apply a tangential stress. If you have an elastic solid, the material reacts to the external tangential stress with some finite angular deformation. Okay? So for a finite value of tau, you have a finite value of gamma. And when you remove the external load, the angular deformation goes back to the original unstressed value, which is 0. In contrast, if you have a fluid, when you apply a finite tangential stress, you get an angular deformation which grows in time. And this is not sure that it is finite, because if you stress for an infinite time, this angular deformation grows indefinitely. However, for a given material, there is a finite rate at which this angular deformation grows in time. And this is the quantity we use to parameterize the behavior of the material. So a fluid is a material which reacts to an external tangential stress with a finite angular deformation rate. And when you remove the external load, you don't recover the initial configuration. Now, having said this, we need to specify that not all the fluids react to an external tangential stress with a linearly growing angular deformation. So there are some of them which react like this, some others which react like this. Well, some others depend on a nonlinear function of tau. So the easiest, the ones that I've described here, are called Newtonian fluids. We will devote a lesson to what happens to different fluids that do not obey to this simple relation. Good. So this is just to specify what do we mean by a fluid. Now, as you can see here, I never mentioned what happens to the volume. By the way, a small question that you can answer mentally or in time. What happens to the volume of this sample as I shear the material? Okay, you might take some time to think, but the answer is trivial. The volume remains exactly constant. Why? Well, we know there is a theorem in geometry which tells us that a rectangle is equivalent to any parallelogram with the same base and the same height. So regardless how much I shear this material, the area will be always the same. So this area will be identical to the sheared area. So this means that the volume of this material will stay constant in time, no matter how much I shear this sample. However, this is not relevant for this discussion because I never mentioned what happens to the volume. Neither I mentioned whether this is a solid, a liquid, or a gas. Okay? So all we need to do to a material in order to understand, to classify it, and to understand whether or not it is a fluid, is to take it, to apply a tangential stress, and to measure its deformation. When it is constant and finite, it is a solid. When it grows continuously in time, and the material does not recover its original position, then we are handling a fluid. So once we have understood that fluid does not relate to the organizational matter, we can list some simple example. So you have water, and water, there is no doubt, it is a fluid, because when you shear, you can keep shearing, and it deforms. When you remove the external shear, the material does not recover its original shape. Then gases. Gases are definitely a fluid because you can mentally think to have in between your hands a block of air, and when you apply the shear, it deforms. Now you cannot see it, but mentally you can imagine that air is doing exactly this deformation. And once you remove your hands, the air block remains sheared. But also some other unsuspected materials behave as a fluid. For example, tar, the one you lie on the street to drive comfortably, that is a fluid. And then you might think, what the hell? If it is a fluid, why do I drive a car and I don't ride a boat? Well, the point is that, and this is quite an important point, I never mentioned what is the magnitude of this gamma dot. So the angular deformation rate might be so small that on our everyday scale we don't appreciate it. So this is a rate between an angle and time. So this would be radians per second or degrees per second. Okay? So when you shear water or hair or oil or honey, then your angular deformation rate is likely to be some degrees per second, some radians per second, and then you can clearly appreciate just by looking at the deformation that the material is shearing. But what about a material whose angular deformation rate is 1 arc second per century. So 1 arc second is 1/60 by 1/60 of a single degree. So the arc second in itself is a very tiny angle, and then you impose this very tiny angle to be achieved within a century. There is no hope on our lifespan that we appreciate by eye, this angular deformation, but nevertheless, if this were 1 arc second per century, and after a couple of centuries you would have doubled the deformation, after 3 centuries you had tripled the deformation, and when you remove your external stress, you don't recover the original position, well, that material as well complies perfectly to this definition. And then that would be, by definition, a fluid. So this happens to tar, and the deformations in the tar material are much larger than 1 arc second per century, and they depend on temperature. But glass, the glass who is shielding your windows, is a fluid. The shear is applied by gravity, and over the centuries it tends to drip to the base. Fortunately, the dripping rate is so slow that it is more likely that the glass layer gets broken by some bad boy with a stone rather than our plate completely drips to the base. And this is why in our everyday life we consider glass as a solid, but from the material structure it is indeed a fluid. Ice is another material which usually we perceive as a solid material, but as a matter of fact it is a fluid. And you can see in the geysers on the mountain that the tongues of the geysers tend to flow through the valleys, and they flow at different rates depending whether they are close to the boundaries or at the center of the tongue. Well, we will make other examples in the future. So for the time being, let's focus on these two materials, so elastic solids and Newtonian fluids. Now we have to understand why they behave so differently. So usually a philosopher or someone involved in humanities, usually he or she is able to explain things just by giving convincing arguments. And this is not the case of a scientist or an engineer. So an engineer not only has to give an argument to put in a frame, but an engineer has to understand. So now we realize that there are such different behaviors, but we want to know why it is so. What is the cause of this so different behavior? So the cause for such a different behavior is in the microscopic organization of matter. So we know that matter can be organized at a microscopic level in very different ways. You might know that gases are, as a matter of fact, molecules or atoms very far apart. They move in a chaotic way at very high speeds, order of hundreds meters per second, and very seldom they collide each other. So once they collide, they change trajectory, and these collisions are quite rare, of course quite rare on a microscopic scale. Solids are completely different. So solids are made by these atoms or molecules who occupy very precise positions, and they have tiny oscillations around these positions, and their distance is kept fixed by some kind of bond. Now this can be ionic bond, covalent bond, metallic bond, so there are many different kinds of bonds, but the final result is that microscopic, the atomic units of a solid, keep these units at a constant distance. Liquids are in between. So liquids are neither as ordered as solids, nor as chaotic as gases. Okay? So liquids are somehow the toughest to study, because you can neither apply the relations of standard mechanics nor the ones of the statistical mechanics. So actually liquids might thought of as materials that have not decided yet what they want to be. So they would like to be like gases, completely chaotic, but they are not energetic enough. And so every now and then they tend to arrange and organize in tiny structures like solids. Now, of course, these are words, but we need to stick to relations. And then how do we formalize, how do we put in formulas and graphs this behavior? Well, fortunately, there is a quite simple theory. Well, actually, the theory is not simple at all, but the final result is definitely more handy, which is the Lennard-Jones potential and force. So let's try to quickly revise it. You know that all the matter is made by elementary units. Now this might be atoms, molecules, ions, atomic particles. But if you look close enough at the microscopic level, matter is not a continuum substance, but it is rather made by distinct, discrete microscopic units. Okay, so you see this blackboard, which looks solid and smooth and regular, but if I had a microscope powerful enough to look at the, say, nanometric level, well, I would see first a very rough surface, and eventually I would see that there are units kept together by some bonds. So here, for example, this is a solid. It is very much likely that I would see some units at some very regular position, and these units would just, well, of course now I am oversimplifying, but these units would just vibrate around an equilibrium position, but on the average they would keep the position constant. So something we could do is to ask ourselves, if I indicate by r the distance between any two of these units, how do the force exchanged by these two units depend on the position r? Now let me sketch a plot first, and then we will comment it. So I can put on this axis the distance between any two of these units and the force they exchange. So a very general behavior would be something like this. Would be a force like this. Now let me use a different color just to highlight this curve. Now it is very clear here, but here it has a specific behavior, so it tends asymptotically to zero from below. Now the meaning of this force is that the force is repulsive when it is positive, and it is attractive when it is negative. Okay? So the sign and the magnitude, the direction and the magnitude of the force between these two units depends on the distance. So when they are very far apart, the force is essentially zero. When they are very close, the force, so when the distance, when r tends to zero, the force tends to diverge, tend to become infinite and positive. So there is the repulsion between the units, and in between there is this peculiar behavior. So it is attractive up to some point. It is zero at this specific distance, which we can call lambda, and then it becomes attractive when the distance increases. So let's see a little bit better what happens for the interatomic or intermolecular forces. Actually, you know that any atom or molecule has a nucleus, and then there are electrons. So this part, the attractive part, is due to the van der Waals dipole forces. So essentially, there are nuclei which attracts nuclei who are electrically positive, tends to attract the electrons of the other unit who are negative, and so there are these attractive forces. However, when you get to some distance, then electrons tends to repel, and also nuclei who are not shielded anymore by electrons when they are too close tend to repel. And then there are these short distance forces who tend to become violent and repulsive. Now you might have noticed that there are no numbers on this graph. Why did I do so? Because while it is a general behavior from a qualitative point of view, the quantitative part depends a lot on the specific material. So iron has some behavior, but tungsten or copper or aluminum has a different behavior, but rocks have a different behavior, wood has a different behavior, and so on. So I don't want here to commit to any specific material. And I should also say that this relation it does not come from an exact theory, but it is rather an empirical relation which was laid down by John Leonard Jones. So he was just a single scientist. Actually, he was a mathematician, a physicist, and also a chemist. He's considered the father of computational chemistry. He lived in between the 19th and the 20th century in Great Britain. And actually he conjectured that the forces between two microscopic units are ruled by a potential function of this form. So U as a function of R, this would be, I hope I don't write anything wrong, because I'm just going based on my memory. So it would be sigma by R to the power 6 minus sigma by R to the power 12. So this epsilon is the depth of this well. Sigma is the radius of the sphere approximating the atom or the molecule, and these 6 and 12 powers are sort of empirical relations. So actually I believe that this 6 has some theoretical ground, but this 12 is purely empirical. So now keep in mind that these are not forces, this is a potential. So the force vector is minus the gradient of a potential. So the gradient of a scalar is a vector, so this is a vector force. But now this potential depends only on the radial distance. So this is nothing but minus du dr times r versor, where r versor is the direction of the segment joining the two units. Okay, so this would be r versor, and you can easily make this derivative, and you end up with a formula which would be 4 epsilon. Now don't blame me if I don't remember correctly, but it would be 6 sigma to the power 6 by r to the power 7 minus sigma to the power 12 by r to the power 13. And then, of course, there are numbers, so there is a 6 here and a 12 here that could be also gathered. But let me see, there is a minus here, if I remember correctly. Oh yes, there is a minus here. And, well, once you put everything together, you get this formula, and this formula accounts for this shape. Okay, this is just to give you a flavor of the origin of this line, of this plot. But now, what does it imply physically? And this is the interesting part of the story. Let's start from the solid. So a solid, if we look microscopically inside, we find something like this. And we realize that by magic, the distance between these units is just this equilibrium distance. Now, why do I claim that this is an equilibrium distance? Well, the argument is extremely simple. A configuration is an equilibrium configuration if, when I perturb it, the system tends to recover its original configuration. Now, think of this system in which I try to pull the units apart. What am I doing? I'm increasing the distance. So from this point, I move here. But if I move here, I generate an attractive force. And the attractive force tends to restore the equilibrium configuration. What happens if I push the units close? Well, I'm moving here, and then I'm generating a repulsive force. Okay? So this repulsive force will tend to repel these two balls and to restore the initial configuration. So, in a solid, in an elastic solid, the units are organized in some precise way, and they tend to keep precise distances. Now, there is no reason to believe that they are squares or cubes. They might be much more complex, but the idea is that the shape is quite ordered with the units at some specific distance. Now, let's think again at this mechanism. So when I pull them apart, they are attracted back. When I push them close, they are repelled back. So what kind of bond do I have in between these two units? Well, we can imagine this is a spring, because a linear spring, what it does exactly is that it exerts a force which is proportional to the displacement, and it always acts to react against the displacement. So when I compress, the spring pulls back. When I pushes back. When I pull, the spring pulls back. Good. So I can think of this system having a sort of springs among the units. Okay? And this is the undeformed configuration. So every unit has exactly the same distance, lambda, there might be tiny oscillations about the equilibrium position, but nothing happens. Now what I do, starting from this undeformed configuration, I start shearing. Well, when I shear, let's pretend that this is the microscopic unit. When I shear, the unit shears as well. And you might recall that an angle is an intensive quantity. Okay, so it doesn't depend on the size of the system. Or if you wish, we can have a similitude between these two triangles. So if I shear by an angle gamma, any tiny macroscopic element will be sheared by the same angle. So I can imagine that this, well, let me use a different color. So I can imagine that my initial square will be deformed into this slanted parallelogram. Now, what is the consequence? Well, these two units are just shifted by the same amount. So their relative distance is exactly the same. So if it was initially lambda, it will be lambda as well. So lambda is here, the force is neither positive nor negative. So these two units are still exchanging zero forces. However, this is not the case for these two units, because this edge now has become the hypotenuse of a rectangular triangle, and we know there is a theorem which tells us that the hypotenuse is bigger than any other edge of the triangle. So it means that this spring has been stretched. So the distance has increased. It means that I moved from here to some larger distance. And when the distance gets larger, there is an attractive force. Okay? So this spring would be attracted towards this one. And this spring would be attracted towards this, unit. Of course, the same will happen to the other, and here there will be other forces. Now, what happens to this unit? As you can see, this force will have a horizontal component, and this force will have a horizontal component. And this is what opposes to the external load. So we have a horizontal vector on every unit, and this horizontal vector sums up for all the units. So eventually, when the composition of all these units will balance the external force, the system will stop shearing. So what happens is that I start from this block, I start shearing. The more I shear, the more this component increases. We can sketch here. So if I deform in this way, this vector will increase in length because the distance will increase, and also its horizontal component will increase, and this keeps increasing until the resultant of all these horizontal forces will oppose exactly the external force, and the block will stop shearing. So this explains why in an elastic solid, when I shear, I can shear also up to a finite angular deformation. Because when I exceed the total force, I have no more driving to keep shearing the element. Now what happens when I remove the external force? We saw externally that the block recovers its original position. So why is it so? Now it is trivial to realize that these forces do not have any force to counter, and so they start moving back. And the more they recover the original position, the more this reaction shortens, decreases, and when they recover back the original position, the force is zero again, because all the units are back to the original lambda position. Now, of course, it's not so simple, because when I have sheared, I've done some work. I put some energy into the system, so my force has displaced the element in the same direction, so force times displacement is work. I put some energy into the system. The system has stored the energy into the deformation of the springs, so when I remove the external force, these springs accelerate the system to the equilibrium position, so the system attains the equilibrium position with some kinetic energy, because the system has accelerated, and so it overshoots and starts swinging, starts oscillating between the equilibrium positions. Of course, there is some internal friction, and at every swing, part of the energy is dissipated into heat, and so eventually, after a few nanoseconds, these oscillations are damped out, and all the energy has become heat. Okay, this is something that probably you already knew, and this is the reason why solids behave in this way. This is why solids, when you apply an external force, can have only a finite deformation, and when you remove the force, they recover the original position. Of course, this is true only if the deformation is small enough to stay into the linear part of this curve. Otherwise, you attain plastic deformations and they become permanent. Good. What happens now to the fluids? And this is quite more complex, because for the fluids, we are not even sure what is a fluid. So, is it a liquid? Is it a gas? Is it something that we perceive as a solid, but in fact is not a solid? Let's start from the easiest possible fluid, which is a gas. Okay? So gases are here. Gases. Actually, I should say gases are here, so they are so far on this line that they wouldn't fit into the blackboard. What do I mean? A gas can be thought of as a collection of balls, and these balls have chaotic velocities. Well, I'm just sketching random arrows. And these velocities are quite high, so they are hundreds of meters per second. So for air at standard temperature and pressure, the average magnitude of these velocity vectors is of the order of 400 meters per second. So why we are not swept by a tornado? The reason is that these velocities are in all possible directions. So the average, the mean velocity that we feel of the air is 0. So today is quite a hot day, and I'm sweating. The reason is that there is no mean motion of the air, which is taking away my heat, despite the fact. So we were saying, how comes that despite the very high velocity of the single molecules of a gas, I don't feel my heat be taken away, because our body, our receptors on the skin just perceive, just are sensitive to the mean velocity. And there are so many molecules, we will come to this point, that for every one going in this direction, there is another one going in the opposite direction. So we have the single molecules who are traveling at hundreds of meters per second, but the overall average velocity is 0, and this is why we feel this still air. So how is it possible that a medium made of all these units traveling randomly in space behaves like a fluid? So something that deforms continuously. Let me make a zoom of this behavior. So we have the upper boundary that I can indicate by an orange boundary, and then we have the fluid. So what I do, I discretize. This is the initial shape. I discretize, I divide the fluid sample into some layers of finite but small thickness. Now, within each of these layers, there are millions, billions, hundreds of billions of these molecules, and the velocity distribution of all these molecules is such that when I don't apply any forcing from outside, the average velocity is zero. So, for example, we can think of a molecule having a velocity like this, and another one, for example this one, having a velocity like this. So when we make the vector sum of these two vectors, the average is zero. Of course, it's not just two, but billions with a random distribution of velocity directions and magnitudes, so that the average is zero. So when I see from outside, from my macroscopic world, that the fluid is at rest and is not deformed, it means that in every layer the molecules have zero average velocity once I make the mean of all of them. Now, let's focus on one single molecule. For example, this one. If the upper boundary is at rest, so zero velocity, its trajectory would be something like this. And then, after the rebound, the velocity vector could be, for example, this velocity vector. However, since the upper boundary is moving with some velocity, because the block, as a consequence of the application of the shear stress, is deforming continuously in time, we have a velocity. Now, because of this velocity, the trajectory of this test molecule will not be the one that I just sketched, but will be this other one. Okay? And the velocity vector will not be the white one that I have just drawn, but will be the cyan one, the light blue one that I've sketched right now. It's like having a moving belt, like the one when you exercise, you practice in a gym. If you have a rubber ball and you bounce with the belt at rest, you have a perpendicular rebound. But if it is moving and you try to throw a ball like this, the rebound will be in this direction. Here we have exactly the same dynamics. So every molecule that would have rebounded perpendicular now will have this velocity component. Now, think of just of this single test molecule. If before the average velocity were zero, now we have a perturbation. And this perturbation is biased towards the velocity of the wall. And the same argument can be repeated for all the molecules who are going to rebound against the wall. So all of them will have a bias towards the right. So if you put in motion the upper boundary and then you make an average of the velocities of the molecules here, you will have an average velocity which now is not zero. Well, let's call it v prime because it's not the same as v. And now, after the rebound, these molecules will cross the boundary and go to the lower one. And again, these molecules will bring this bias towards the lower layers. And so here, before we had zero average, before we started the deformation, and now we will have another velocity, which we can call v second. And again, new molecules will cross the third layer, and then we will have a third bias, which we can call v third. And the process continues. We can divide our fluid sample in many layers until we go to the very bottom. Now, what happens here? Well, we can repeat the same argument as the moving boundary, except that now the boundary is at rest. Our plane is fixed, And so all the molecules bouncing against this fixed boundary will have to will have to bring a zero average through the fluid. So it is somehow an agreement between a boundary moving towards the right at velocity v, and somewhere here a boundary at rest with velocity which is 0. And then the equilibrium solution would be a linear velocity profile, which is the reason why we have this angular deformation rate, which leaves a straight surface into a straight, although slanted surface. Now keep in mind that this is not a proof, this is just a convincing argument. Okay? Actually, it is possible to prove analytically that a linear velocity profile is an exact solution of the governing equation of the fluid motion. If you are curious, it is called plane Couette flow. It is very much likely that we will not cover this topic. We will not get that far in this first month of lessons. But if you are curious or if you want to know, just let me know and we can arrange an explanation. So, to summarize, the very relevant piece of information is that for gases, so for fluids being somewhere here, so that the intermolecular forces are irrelevant, we don't care about what happens when they are too close. However, we must care about collisions. And these collisions are such that when a molecule bounces against a moving boundary, this velocity information is diffused throughout the various fluid layers, and this induces a linear velocity profiles. However, these bouncing molecules do not have permanent links. So, if at some point I decide to stop the boundary and to remove the external forcing, from that moment on, I will not have any velocity to be diffused throughout the fluid, and so the angular deformation will stop. But at the same time, since there is no permanent connection among the molecules, there is no way for the fluid layer to recall what was its original shape. And so, since there are no forces, there is no possibility for the fluid layer to recover its original position. So in other words, every instantaneous configuration is an equilibrium position for the set of molecules. So when you remove the external forcing, the latest configuration is the configuration the fluid layer will keep for good, unless some other external perturbation sets in. So this is what happens for gases. And then we have covered somehow the two extrema of the possibilities. So what happens here for elastic solids when everything is ordered and well defined, and what happens here for gases when molecules are so far apart that they don't have any connection each other. Now, what happens for a liquid? First of all, what is a liquid and why a liquid has such freak behavior? Well, first of all, let's consider for a second water, which is the most common liquid we have at hand. So we know that water is at a liquid state, at least at ambient pressure, if temperature is in between 0 and 100 degrees Celsius. Then what happens above 100 degrees, we know that boiling starts, and if we keep a sample of water boiling, eventually it becomes all gas. What happens below 0 Celsius? Well, water freezes and it solidifies. Now, we have mentioned before that it's not really an elastic solid, but at least at the first level, for our perception, it is a solid. So what happens? Think of any two molecules of water. Okay? This is a partial view of what happens, because on top of this diagram giving the forces versus distance, there is also another dynamics, which is the oscillation. Okay? So every molecule, as a matter of fact, is not fixed at its position, but every molecule oscillates. So here, we shouldn't see this as an instantaneous configuration, but rather as an average configuration. So if we were able to shoot pictures of this system time after time, we would see that every unit would oscillate around its equilibrium position. Now, for elastic solids, these oscillations are so tiny that the restoring forces are able to keep each unit bounded within a certain position, so that the average is well defined. Now, if you increase temperature, as you increase temperature, you increase the amplitude of these oscillations, and as you can see, while the repulsive force keeps increasing, actually it increases even more severely, so eventually it becomes vertical, the attractive forces quickly saturate and then decrease. Then this means that when two units approach each other, the repulsive forces can grow indefinitely, so that they can never get close to each other, but when they come far apart, after a while the attractive force decreases and eventually it vanishes. So what does it mean? When you have two units, if the oscillation amplitude is big enough, when they get close, you can establish a link, which is nothing but this repulsive force, but when they move very far apart, this attractive force goes to zero, which you can think of having the spring which breaks off. So in a liquid you have this metastatic equilibrium in which when two molecules get close, they establish this spring-like connection, but when they get far apart, they are so energetic that they can break the spring, and then each unit is free. So it looks more like a gas than like a solid. Now, since the single molecules or atomic units have a distribution of velocities and a distribution of energies, it happens that some molecules are connected and some others are loose, so they are free to move. So in other words, a liquid can be thought of as a material which has too much energy in the molecules to behave like a solid, but at the same time too little energy to behave as a gas. So a liquid is a sort of metastable state of matter that can only exist within a limited range of temperature. And water is a very common example. Only between a given range you have liquid water. Above some threshold you have gas, below some threshold you have a liquid. And the same, if you make up your mind, the same is true for any material, even a metal. A metal, above some temperature melts, and then you have a liquid, but if you keep increasing the temperature, it starts boiling, and so eventually it vaporizes. Okay? And even a gas. If you take even hydrogen, hydrogen is the lightest gas we have, but at some point it liquefies, and when you get close to the absolute zero, it becomes solid, a sort of ice. Okay, so how do we parameterize such a freak behavior? Well, a liquid can be conceived as a sort of mixture of materials in which you have islands of solids, which are the subsets of molecules that are establishing some links for a given time. And these molecules are surrounded by a sort of ocean of loose molecules. And these molecules are those who have temporarily broken the connections, the bonds between the nearby molecules. To complicate further the picture, there is the time dependence. So this configuration changes in times continuously because everything is moving and oscillating. So there are these islands which break up and connects some other molecules or atoms from outside, and some molecules aggregate to form new islands. But the overall picture is that on the average the same volume fraction is solid-like and the complementary volume fraction is gas-like. So a liquid, if now we split, similarly to before, the various layers into different sublayers, we see that when you move a boundary, there are these islands who are dragged by friction by the moving boundary, and just by friction with the lower solid islands, they tend to drag all the other fluid layers. And this motion is somehow lubricated by this ocean of loose molecules, whose configuration changes in time, but changes at a such fast time scale that again every picture, every configuration looks from outside as an equilibrium configuration. Now it's a sort of a kind of magic, but miraculously the overall equilibrium velocity is the same as for gases. And again, it can be shown by analytic solutions of the equations of motion for a fluid. So this is the reason why gases and liquids are somewhere here, although they have more energy, so we would need a third axis here to show how this curve appears when you increase the energy of the single molecules. So liquids at the very end behave very much like fluids for a different microscopic reason, but yielding an identical large-scale macroscopic behavior. So again, for a liquid there is the viscosity, which determines the reaction to an external tangential stress. Now this concludes our first lesson, and just as a hint for the next one, keep in mind that there is a sort of dual behavior. What we perceive from outside, looking at large scale from our macroscopic world, and how the material behaves at a microscopic scale. So the properties that we define for a fluid are the resultant of the atomic and molecular behavior, which we parameterize at large scale, giving some new quantities. So today we have introduced just the first of these quantities, which is the dynamic viscosity. So once again we have written that the shear stress modulus is equal to the dynamic viscosity times the angular deformation rate, and this dynamic viscosity is a property of the material. Now, all the behavior of gases, of liquids, and of some kinds of seemingly solids is included in this parameter. And it is the summary of a very complex physical behavior that just for practical reasons we parameterize in a single quantity. Starting from next time, we will see more features of this behavior. Okay, see you next time.